So next up we have Aravindan.
Thanks.
Probabilistic models for graph partitioning.
Thanks a lot, Arvind. So in this talk, I'll be talking about how we can design better algorithms for different average case models of graph partitioning, and how we can design algorithms for a related problem of learning different probabilistic models for clustering or graph partitioning. And all of this work is joint work with Konstantin Makarychev and Yuri Makarychev. So let me start out by fixing my pointer. Let me start out by defining the class of graph partitioning problems, just so that we are all on the same page. So in graph partitioning, you're given a graph, okay, with edges and vertices, and the goal is to divide the graph into a bunch of disjoint clusters, okay, subject to some constraints which are problem specific. For instance, in balanced cut, you're given this graph, and the goal is to split the graph into two equal parts, or two roughly equal parts, so that you minimize the number of edges that go between these two parts. Okay, or for balanced k-way partitioning, you want to split the graph into k roughly equal pieces, so that you minimize the number of edges that go between the different clusters, and so on. So depending on different constraints, you get different problems, but this is a very general broad class of problems called graph partitioning, and that will be the focus of this talk. So graph partitioning problems are typically NP hard to solve, and they've been a central area of study in approximation algorithms. And so because they are NP hard to solve, typically we design good approximation algorithms for these problems. So here you want to design a polynomial term algorithm which is always within, which outputs a solution which is always within a factor, an alpha factor. Ideally it's a constant. You want it to be as small as possible of the optimal solution for that instance. Okay, so that's the approximation ratio, and this is what we want. This measures the performance of the algorithm. And due to a lot of really seminal works, we have a polylogarithmic in n. N is the number of vertices in the graph. We have polylogarithmic approximations for a lot of these problems in this class. Okay, so on the other hand, from a hardness perspective, we have evidence to believe, based on the unique games conjecture or strengthenings of it, like the small set expansion conjecture, that constant factor approximations for all these problems are unlikely. Okay, so just to summarize, from a worst case standpoint, only polylogarithmic approximation algorithms are known for a lot of these problems, and constant factor approximations are unlikely. And so the obvious question, I mean, given this workshop, is can we do better from an average case standpoint? Okay, so I mean, again, with average case analysis, we need a probability distribution over all instances. And if you want a better average case approximation ratio, the goal is to find an algorithm which will always output, for any given instance from this distribution, you measure the cost of the solution output by your algorithm divided by the cost of the optimal solution, and you want this to be less than alpha with high probability. Okay, so this kind of guarantee typically also implies a good expected approximation ratio, because you can always get a n factor approximation for a lot of these problems. Okay, and the main challenge in average case analysis is twofold. So on the one hand, you want your average case distribution to be rich enough to capture instances that come up in practice. On the other hand, you want much better guarantees than you can get in the worst case. Okay, so this, there's a trade-off between these two. Okay, so before we go into different average case models, so a lot of the models that we look at are basically inspired from machine learning, and here are some examples that you might encounter. So on the left is a collaboration network where you have a bunch of researchers denoted by vertices and edges if these two researchers have collaborated on a paper together. On the right is a protein-protein interaction graph. And in all these kinds of graphs, you see that there are these nice clusters, and there are many more edges inside clusters and few edges between clusters. And this is typically what you want your average case models to capture. Okay, so and your average case distribution will typically generate such instances with many edges inside clusters and few edges between clusters. Okay, and in all these problems, you can look for two different kinds of objectives, or two different kinds of goals. And the first one is about approximating the objective. So for instance, if you're looking at a problem like balance cut, where you want to split the graph into two pieces, where you minimize the number of edges that go between them, here you're trying to find a partition. So you're given a graph that is generated from this distribution, and let's say that there is this planted cut or an optimal cut. So we are going to denote it by H. Okay? And the goal here is to output a balanced partition whose cost is small compared to the cost of the planted cut. Okay, so here the goal is to approximate the objective. That is to find a solution of small cost, and the quality of the algorithm is measured by comparing the cost of your solution to the cost of the planted cut. Okay. So if you have no information about the instance, then the best you can hope for is a square root log n or a log n approximation in the worst case. But if your distribution is nice, hopefully you can get a much better performance with respect to the planted cut, hopefully a constant factor. Okay, so that's the first goal. Now, another goal that you can ask for comes from a machine learning standpoint. A very typical paradigm in unsupervised learning is to assume that the data that's given to you comes from a very nice distribution that is appropriate for the task at hand. So for instance, if you're given points in space, you may assume that your data is generated from a Gaussian mixture model. Or for graph partitioning, so when you have communities in networks, for instance, you assume that the graph is generated by a nice probabilistic model. Okay? And in this case, the goal here is to actually learn the model. So it's not necessarily to find a partition of small cost. Here the goal is to learn the individual communities and to learn the generative model that produced the graph, okay, with high probability. So these are two different goals. So the first goal is something that we are used to in the approximation algorithms community or the theory community. The second goal is more common in machine learning. But while these are different goals, they are very related because typically the objective that you care about, for instance, the balance cut objective, corresponds to the maximum likelihood estimator for the probabilistic model at hand. Okay, but this may not always be true. It depends on the average case model. But typically, if you can get a good approximation for the objective, it also translates to recovering the community if the distribution has a nice structure. Okay, so throughout this talk, we'll be looking at both these goals, and I'll talk about different average case models and whether we can find good approximations to the objective and whether we can learn the model and recover the communities. Okay, any questions so far? Okay. So let's start out with a very simple average case model for graph partitioning. So this is called a stochastic block model. So for balance cut, you have these two pieces of equal size. Let's say that they are of size n each. And this is a hidden partition that's not given to you. Okay? And the edges in the graph are generated as follows. With some probability q, which I will denote as b over n. We'll see why it's b over n in a bit. With some probability q, there is an edge between any two vertices in different sides of the cut. So for any two given vertices one from L and one from R, there's an edge between them with probability q. Okay, and you do this independently at random for each pair of vertices from L and R. Okay. Similarly, with between any two vertices in the same side of the cut, so in the same cluster L or R, there is an edge between them with probability p, which is a over n. Okay, so and a is chosen to be larger than b, so you will have many more edges inside the clusters than between the clusters. Okay, so because of this choice of parameters, the average degree of a vertex on the left, okay, so within its own cluster is going to be a, and the average number of edges that go across the cluster is going to be b. Okay, so just to ensure that we're all on the same page. Okay, and this kind of a model is called a stochastic block model, and it's just represented as, using this notation, it just means there are n vertices in each of these clusters. There are two clusters. The average degree inside the clusters is a, and between the clusters is b. Okay, and then you can generalize this, and here the goal is to recover. For instance, if you look at the second goal here, the goal is to recover the two communities, L and R. And if you find the two communities, you can also figure out the parameters P and Q. Okay. You can also generalize this to k-way partitioning, where there are k communities of equal size n. So the total number of vertices is n times k. So it's a very symmetric setting. And again, edges inside these clusters are present with probability p, which is a over n. And edges across clusters are present with probability q, which is b over n. And a is greater than b. And so a is the expected degree of a vertex inside its own cluster, and b is the expected degree of a vertex to a certain other cluster. Okay, so if you fix two clusters, b is the average degree from a vertex to a certain other cluster. Okay, so this is the setting. Okay, and here remember, every edge is chosen, every edge choice is chosen independently at random. Okay, so this is a stochastic block model, and there's a lot of work on stochastic block model across different communities in statistics, in theoretical computer science, and so on. And it has also been generalized to handle different edge probabilities inside clusters and between clusters, or different expected degrees and so on. There's a lot of work on stochastic block models. And broadly speaking, these different algorithmic results that are known fall under three categories. Okay, so the first are what are known as exact recovery results. So here the goal is to recover the communities exactly, all the community memberships with high probability for each of the vertices. In partial recovery, you care about classifying 90% of the vertices, so 1 minus delta fraction of all the vertices. And in weak recovery, you mainly care about just finding a partition that is better than random. Okay, there's something better than random. Okay, so these are the kind of results that, these are the three broad classes of results that exist, and I'll go over a little bit about each of them. Okay, so a lot of the work on stochastic block models is about recovering each of the communities exactly. And starting from the work of Bopanna in '88 and Frank McSherry and so on. So we know that spectral algorithms, okay, we just find the top k eigenvectors and then project onto them and then cluster based on the top k eigenvectors. They can actually find the two communities as long as there's enough separation between the degrees. Okay, so here, so the square root of a plus b corresponds to the standard deviation when you look at the difference between the number of edges inside its own community and across, to a different community. And as long as a minus b is square root log n times the standard deviation, then with high probability you can recover all the communities. All the vertices in different communities. Okay, and this can be extended to general K, where you get essentially the same kind of result. And this term here is because the standard deviation now is square root of a plus k minus 1 times b. Okay, and where c is some appropriately chosen absolute universal constant. And now we have a very good understanding of what exactly this constant is. So that's a sharp characterization. So if it is larger than this particular constant times the standard deviation, you can recover exactly with high probability. Otherwise, it's information theoretically hard to recover all the community memberships. Okay, so this is about exact recovery. But in all these cases, for these conditions to hold, you need that the average degree should be at least logarithmic in n. Okay, and if it is less than logarithmic in n, you may not even have connectivity in the graph. So you can't hope to recover all the communities exactly. So as long as it's at least log n, these results start kicking in. Okay, but what about the sparse regime? Because a lot of social network graphs, for instance, are sparse. And here, there's this result by Amin Khoja-Aglan who showed that you can actually, even though the graph may not be connected, in the sparse regime you can still find a polynomial time algorithm that finds the minimum balance cut, as long as there is sufficient difference between the inside cluster degree and the intercluster degree. Okay, and of course you can't hope to recover the memberships exactly, but in the series of works they were able to show that you can recover the community memberships up to delta fraction being errors, as long as there is this much difference in the degrees, okay, the inside cluster degrees and the between cluster degrees. You don't need to focus that much on the exact relationship between A, B, and so on. It's just to give a sense of the kind of results that, the kind of conditions that you need about these degrees. Okay, so these are partial recovery results. So here, these give a smooth kind of a guarantee, because if you substitute delta being 1 over n, you recover the exact recovery guarantees. Okay, and and the last line of work is about weak recovery, where the goal is to basically try to output some partition which has non-trivial correlation with the planted partition. Okay, so for k being 2, you just want the partition to have more than half correlation with the with the planted partition. And here, due to these amazing results by Mosul, Neiman, and Sly, and Masoulier, they showed this sharp phase transition that occurs. So as long as a minus b divided by the standard deviation is larger than 1, then they give a polynomial time algorithm that can output this this partition with non-trivial correlation. And if it is less than 1, then it is information theoretically impossible to do so. Okay, so these are various results that are there about stochastic block models. I only focused on symmetric stochastic block models, but a lot of these results also, not the sharp characterization, but they also exist for various generalizations of the stochastic block model. Okay, and the focus of this talk will be about partial recovery. We won't be looking at exact recovery. Okay, so there's a lot of this nice work on various stochastic block models. There's of course a fair criticism from an applied community, and the criticism is that you never expect data to be generated exactly according to a given model. Okay, there's always noise. And so there may be different kinds of noise. For instance, there may be outliers or corruptions in these edges, or the given model is not really a good fit. So you're not given a graph that is generated exactly according to a stochastic block model, but it comes from some other probabilistic model that's close to a stochastic block model. So there's just some model misspecification. Okay, and you want your algorithms to be robust to this kind of noise. And I think it's in some sense, I think it's a very important criterion in picking a good learning algorithm. You want your learning algorithm to be robust to noise. Yes?
So has anybody done an empirical study of SBM type models? Because they make a specific prediction, right? Where the edges will be.
Okay.
Like
predictive, yeah.
So have people done that study, and what do they find? Is SBM at all a reasonable model for social networks or anything?
Yeah, actually, I don't know, actually. So in the sense that I think people agree that it's not a good model for social network graphs, because in social network graphs you see things like
Triangles.
a lot of triangles, large cliques, and so on, dense subgraphs, and so on. So an SBM is not a good model for these.
Yeah.
But perhaps in other settings it is a reasonable model, like biological networks or something else.
It's just surprising that they've been around for 20, 30, 40 years and nobody's done that study.
Well, yeah, there must be, but I actually don't know about work along this direction. Okay, so, and you could ask, okay, how robust are usual approaches? For instance, if you look at spectral clustering, which finds the top k eigenvectors of your graph, the adjacency matrix of your graph, projects and clusters them, then these kind of spectral methods are very brittle to noise, because you can just corrupt a few edges or a few entries in your matrix, and your spectrum can go haywire. Okay, so in this sense, spectral methods are not very robust, and so are methods like counting paths and random walks and so on, which are often used to get these kind of guarantees for stochastic block models. Okay. On the other hand, in the statistics community, maximum likelihood estimators are typically used for learning various probabilistic models, and they have some good robustness properties, because typically they find the best fit probabilistic model measured in KL divergence, okay, even if there's modeling error. But however, the problem with maximum likelihood estimation is that it's typically NP-hard. For instance, for probabilistic models, it just corresponds to finding the minimum balance cut. Okay, so you want algorithms which are polynomial time algorithms, which are also robust to various kinds of noise and modeling errors. Okay, and finally, I mean, just as Sanjeev was mentioning, stochastic block models or these kind of simple random models are not very, do not have the kind of properties that real-world graphs do, because they assume a lot of independence. And real-world graphs, for instance, have heavy tail degree distributions or dense subgraphs, large cliques, and so on. And these are not properties that are exhibited by the stochastic block model or simple random graphs, additionally random graphs. Okay, and so you want more general average case models that can capture these kind of real-world graph properties. Okay, you want to assume as little as possible about your average case model and still show good provable guarantees. Okay, so I'll do this in this talk in, in two different ways. So first, I'll talk about different average case models, like semi-random models, that started with this work by Feige and Kilian. And we'll talk about how you can incorporate different kinds of adversarial choices into your model and how you can make them more and more general. Okay, so here, the focus will mainly be on approximating the objective. And in the second part of the talk, I'll talk about how you can handle different kinds of modeling error. You can assume that your graph is drawn from a stochastic block model, but some kind of with noise. So you have various kinds of modeling error, and I'll show how you can recover the communities up to good accuracy in that case. Okay. Very good. So the first semi-random model for graph partitioning was the one that was proposed by Feige and Kilian. So they came up with this really nice model where you assume that your graph is first drawn from a stochastic block model, or the standard partitioning model. But additionally, an adversary can then come and delete edges between clusters or add edges inside clusters. Okay, so these kind of changes are only monotone changes, because just deleting edges inside clusters or deleting edges between clusters or adding edges inside clusters only makes your planned solution even better. Okay, so this is called a monotone adversary, and the question is whether these algorithms for learning stochastic block models still work in the presence of a monotone adversary. Okay, unfortunately, we don't know that spectral algorithms do, but Feige and Kilian showed that you can use STPs, semi-definite programs, to make these spectral algorithms robust. Okay, they showed that under essentially the same kind of conditions about the difference between the inside cluster degree and between cluster degree, perhaps with a slightly worse constant, STPs will actually recover the community memberships. So it does both the job of finding the optimal solution and learning the community memberships. Okay, so this is about monotone adversaries. And this has been extended to K-way partitioning with similar guarantees as well. Okay, and all these algorithms use convex relaxations like semi-definite programs. Okay, so you could ask, okay, so monotone adversaries only seem to make your life easier because your planned solution only becomes better. So is there a formal way in which this is true, a formal sense in which it's true? In a surprising result by Moitra, Perry, and Wayne, they showed that, in some settings, having monotone adversaries actually make your life harder, in the sense that you have these phase transitions for weak recovery for a stochastic block model. They showed that when you have a monotone adversary, you can construct a monotone adversary such that the threshold under which weak recovery is possible becomes worse. Okay, so while intuitively it seems like monotone adversaries should only help you, they actually show that with monotone adversaries, there are settings where it actually becomes worse. Okay, and there are lots of interesting open questions about monotone adversaries. I think one nice question is, do we actually need semi-definite programs to get algorithms that are robust to monotone adversaries? Can simpler algorithms like spectral methods, or can you come up with modifications of counting-based approaches that actually work with monotone adversaries? And however, one issue with monotone adversaries is that, while you get some adversarial nature because of these monotone changes, the model still assumes a lot of independence. Okay, and if you look at the kind of proofs that are involved, it uses strong properties about the spectrum of the graph. Okay, and so essentially, each of these edges are chosen independently at random. And you can't have triangles that go between different clusters or dense subgraphs that go between different clusters. And you'd like your average case models to be more general enough to capture these kind of settings. Okay, so here's another semi-random model, which is a little more general than monotone adversaries model. So where here the goal is to capture arbitrary correlations inside clusters. Okay, so here there is this planted partition L and R, and you have arbitrary edges inside the partitions, and the edges between the partitions L and R are random. Okay, so here you can think of it as essentially think of a perfect partition. Okay, so this is L and R, so you have whatever edges you want inside L and R, and nothing between L and R, and then you have random noise between the clusters. Okay. So this is more general than the Feige-Kilian model in the sense that you have arbitrary edges between. Okay. And you can show that under this model, for various problems like balanced cut or k-way partitioning and so on, you can get a good constant factor approximation. Okay. So this is getting close in objective. Okay. So as long as the number of edges is at least, so as long as the average degree is at least square root log n, you can get a constant factor approximation. Okay, so this is about the first goal. Then you could ask, what about the second goal? That is learning the underlying ground truth partition. And so unfortunately, because you can have arbitrary correlations inside the clusters, ground truth recovery is impossible. Okay, just because you could just have a GNP graph inside, and edges with probability p between. Okay, so and in this case, you can't hope to recover the underlying partitions. And so in general, you can't recover the underlying, the partitions unless you have some kind of expansion properties inside the clusters. And so what we can show is that as long as you have good expansion properties, that is the expansion inside the clusters, I won't formally define the notion of expansion we use. As long as the expansion inside the clusters is a constant times more than the expansion of the planted cut, you can also recover the communities up to good accuracy. So you can do partial recovery.
What do you mean by need expansion? The need assumptions?
So if you don't have, suppose you have a very sparse cut inside, then you can just move the cut to the other side and you're not actually losing anything in the cost. So you do, so expansion assumptions are necessary. Some kind of expansion assumptions are necessary. And assuming this kind of an expansion assumption, you can recover the communities. Okay. So this is nice, but however, it's the graph between the two clusters is still random. Okay, and we like to get rid of this. So here, joint work with Makarychev and Makarychev, we propose this model called the random permutation invariant edges model. So this is the model. So here, you think of this graph as being split into two parts. Okay, so there is this planted partition L, R that's not known to you. Okay, so you think of it as being split into this graph inside clusters plus a graph that is between clusters. Okay, so and ideally we'd want the edges inside clusters to be completely arbitrary and the edges between clusters to also be arbitrary. Okay, but that's not possible because that would be a worst case instance. So what we'd instead assume is that the inside cluster edges are arbitrary, and we'll just assume that the between cluster edges come from any distribution that is permutation invariant. So what do I mean by this? I just want this graph that comes between clusters to come from any distribution that doesn't depend on the identity of the vertices. Okay, so one way of generating such a graph is think of an arbitrary graph inside the clusters, think of an arbitrary graph between clusters, and you just randomly relabel the vertices here. Okay, and just fuse the two graphs together. Okay, so that's a graph that comes from a permutation invariant distribution. Okay, so what's the advantage compared to previous models? Well, it's more general, but it's some way of capturing independence between the inside cluster edges and the between cluster edges. Okay, because you would think that edges come from multiple, edges in a social network could come from different kinds of relationships, maybe work relationships or sports and so on, and these edges should really be independent of each other. And this is just a way of capturing this independence between inside cluster edges and between cluster edges. Okay, but more concretely, this intercluster edges could capture complex distributions, so they could come from your preferential attachment models or your favorite kind of an average case model that is just that doesn't really rely on identities of labels of vertices. It's some kind of a symmetry property. Okay, so you can have large cliques or dense subgraphs and so on between clusters as well. And so what we can show is that we can give a constant factor approximation for graphs that are drawn from the pi model, as long as the average degree is at least log square n. Okay, so the way I'd like to think about it is that this algorithm, okay, so in some sense it says that minimum balance cut is easy as long as your graphs come from any average case model that satisfies this permutation invariance property, some kind of a symmetry property. And so, there are quite a few open questions here. So this is just, the first and, potentially multiple things that you could do. So you could ask for guarantees for k-way partitioning. And one thing that we would really like to do, but we don't quite know how to go about it, is recovering the communities when it comes from some kind of a distribution that is permutation invariance. What kind of properties should you assume about the average case distribution so that you can actually recover the communities as well? So you can do the second algorithmic code. Okay. Any questions about this? Yes.
Could you just say a couple of words about what the algorithm is?
Oh, thank you. Yeah. So yes, I didn't go into the algorithm at all. So the algorithm uses semi-definite programming. So the algorithm goes by showing, by using a semi-definite program that's actually the same semi-definite program that's used in the worst case, but it shows some additional structural properties about the semi-definite program. So in particular, it says that the semi-definite program is partially integral. So all the edge weights, so the edge lengths, so the semi-definite program will define lengths of edges, and it could take arbitrary values from 0 to 1. What we'll show is that for most of the edges that are in the planted cut, the edge lengths are going to be at least a half, or large value. It will not be as small as 1 over log n or 1 over polylog n. So that is what allows us to get these constant factor guarantees. Any other questions about this?
Is the log squared there necessary?
So actually that's another thing that we don't know. So for all we know, you could actually do with you could actually get this to work for sparse graphs as well. We actually have no reason to believe that this is necessary.
Okay, something an algorithm you didn't mention is low-rank matrix reconstruction algorithms, which are also used for clustering and balance and partition in random noise models. Just wondering if you also look at it.
I see. So is it kind of related to finding the top k eigenvectors and going about it, or?
Yeah, that's
Okay, so I don't quite know how robust they are. But yeah, that's another approach. It would be nice to show guarantees for those kind of approaches too. So if it's based on things like matrix completion, so I guess it would fit into the convex relaxation approach. And I think, an SDP is actually going to be stronger than such an algorithm. But you're right. So such algorithms are probably more practical, and so it'll be nice to show guarantees for such algorithms as well. Okay, so the last part of the talk, I'll talk about how you can capture modeling errors. Okay, so here it was really about more general average case models, but now we look at the other viewpoint of looking at the unsupervised learning task of learning a probabilistic model in the presence of errors. Okay, so here we like to deal with different kinds of errors. So one kind of error is outliers or corruptions, and another kind of error is model misspecification. And we'll capture this in different ways. So how do we capture outliers or corruptions? So we'll assume that the graph is generated by the following process. So the graph is first drawn from a stochastic block model, as before. And then the adversary has a budget. Okay, let's say that m is the number of edges in this graph, okay, or the expected number of edges in this graph. Now the adversary has a budget of epsilon m. Okay, and this adversary can add or delete edges, add whatever edges he or she wants, or delete whatever edges that have been produced. But in total, the budget should be epsilon m. Okay, so it has a total budget of epsilon m, and the adversary can delete epsilon 2 times m, and can add a bunch of edges. But in total, the number of corruptions that the adversary makes is at most epsilon m. Okay, so you can think of this as a stochastic block model plus constant fraction of them being arbitrarily corrupted. Okay, so this is how you'd capture corruption. We capture corruptions. And then the second thing is about model misspecification. Okay, so here this is related to how a maximum likelihood estimator finds the best fit model in KL divergence. So we ask, okay, so what if the graph didn't come exactly from a stochastic block model, but it came from any distribution that's close to a stochastic block model in KL divergence? Okay, so I'm not going to go into the exact definition. Okay, so here's the definition in case you want it, but so we're just going to assume that it comes from any distribution Q that is close to a stochastic block model in KL divergence up to eta times m. Think of eta as being a small constant, like 0.01. Okay, so this way of measuring modeling error through KL divergence, it also captures adversarial edge additions, but not quite deletions, so they are kind of incomparable. Okay, but this is one way by which, so here now the edges can be very dependent, whereas in a stochastic block model, each edge choice is independent. Okay, so what we can show is that you can get robust learning guarantees of this form. Your algorithm can learn a stochastic block model even if a constant fraction of the edges are arbitrarily corrupted, and if there is KL divergence model misspecification of eta times m, where eta is also a small constant. Okay, so you can tolerate outlier edges, a constant fraction of them being outlier edges, a constant fraction, eta times m distance in KL divergence, and any amount of monotone errors in the Feige-Kilian form. And what we can show is that you can recover the communities up to eta accuracy, where eta has this form. I'm not going to go into exactly what this form is, but the thing that I'd like to point out is that if there is no noise, this is the dependence of the recovery guarantees with respect to A and B, and these are the guarantees that you would also expect in the no noise setting. So it's very comparable to how much you can recover even in the no noise setting. Yes.
Can you give us a sense for how much deviation the scale divergence allows? Like what kinds of structures does it allow?
So for instance, it does allow arbitrary edge additions up to the same eta times m. So, but it's also captured by outlier errors. But you can also do things like modify each edge probability a little bit. Okay, but you can also modify them in a dependent fashion. So yeah, so KL divergence captures both kinds of errors in that sense. So you can think of all the errors as being focused on a few edges, or it could also smear the changes across the graph. Yeah. So that's one. Yeah. So that's one nice thing about KL divergence. Okay, so you can tolerate, you can do partial recovery even when, so up to some constant fraction of them being modeling errors. Okay, and there is some sense in which this is optimal. So if you look at the two terms that come about, one of them comes from a no noise term, and so that kind of a dependence is necessary even if there is no noise. This is necessary even if there is no noise. And this is the noise term, and there is some sense in which, at least for two communities, this kind of a dependence is necessary. Okay, up to constant factors. But I'll not go into the specifics. Okay, so I must say that there's also related work on how you can come up with algorithms that are robust to noise. So there's very nice work by Kumar and Kannan who showed that you can learn various probabilistic models like Gaussian mixtures or blended partitioning models when the noise is structured in some way. And the spectral norm of certain noise matrix has some nice properties. And then there's also work by Kai and Lee who try to capture vertex outliers. Okay, but edge outliers are more general than vertex outliers. So in some sense, our results subsume these results by Kai and Lee. Okay, so in the next 1 or 2 minutes, let me try to give you an overview of the algorithm for just this learning stochastic block models in the presence of noise. So here, it also goes by using a semi-definite program. So you write down a semi-definite program for balanced K-way partitioning. And then what you do is you treat these SDP vectors. I mean, you look at these SDP vectors, okay, the vectors given by the semi-definite program, and then you just apply a simple greedy clustering algorithm on these vectors. Okay, so I'll actually describe the greedy clustering algorithm. I think it's fairly intuitive, so let me describe it now. So before we go there, this is the semi-definite programming relaxation. So you don't need to look at what exactly the semi-definite program is. It just assigns unit vectors to every vertex in your graph. And then it allows you to define the concept of distance between vertices. Okay, so the distance between vertices exactly corresponds to the squared Euclidean distance between the corresponding vectors. So there's not really a distance because we don't impose triangle inequalities, but you can think of them as a distance. Okay, and intuitively you'd think that the vectors that are in the same cluster should be close to each other. Okay, so what we do is we measure. There are two quantities that are very useful. You can look at the average intracluster distance, that is the average over all pairs of vertices in the same cluster of the distance between them, and the average intercluster distance. And what we are able to show is that for a stochastic block model, the average intracluster distance is very small, and the average intercluster distance is very large, is very close to 1. Okay? And this is true even if you have various kinds of modeling errors. Okay, so now suppose, given that we have the structural property, the algorithm becomes fairly simple. What you do is you just take this SDP solution and you apply a greedy clustering algorithm. So what you do is you just look at all the active vertices that are there, okay, and you just look at balls of size of a fixed radius and you pick the heaviest ball that exists. Okay, so you look at balls of radius, let's say 0.1, look at how many vertices are inside these balls, and then pick the heaviest ball that you can find. And then remove this whole ball and then recurse. So it's just a greedy clustering algorithm on the SDP vectors, and we show that this can recover the community memberships up to good accuracy. Okay, and this is based on showing some structural conditions about the SDP. Let me not go into this. Okay, so let me just conclude by saying that, so in this talk, we looked at different average case models for graph partitioning that are more general than stochastic block models and that may allow us to capture real-world graph instances. And we also looked at algorithms for learning probabilistic models for graph partitioning in the presence of various kinds of errors, like corruptions or outliers or model misspecification. And it'll be nice to come up with these kind of guarantees for graph partitioning or other such problems under other natural properties about the average case model. So one way I like to think about the pi model is to say that you get good guarantees as long as your average case model satisfies. It's not focused on a particular average case model. It works for any average case model that satisfies this symmetry property of permutation invariance. It'll be nice to say that you can to identify other natural properties of average case distributions that allow you to get much better guarantees. And it'll also be nice to get these kind of robust learning guarantees for various probabilistic models, other probabilistic models for graph clustering and so on. Yeah, thank you.
Probabilistic invariance is a nice generalization from totally random. Here's another sort of model, right, where the people on the left choose all their friends
but there will be dependence in their choices. So the different people are independent. I mean, this is, so everybody has some characteristics, they choose friends based on that, but
Okay.
the choices are not independent. But different people choose something.
I see.
Now, in the identical case, your thing includes that, but in the non-identical case,
What is identical here?
identical means everybody has the same distribution.
Oh, okay.
Then,
I see.
then permutation invariance is stronger than that, right? But they
Yes.
might be non-identical,
Yes, that's right. Okay.
but independent. So you have
Oh,
n
that's
way
nice.
independence rather than n squared way independence.
Oh, that's a nice way of thinking. Yeah, I haven't thought about it. Yeah, no, I've not thought about it, but that's a very nice property that, we should think about. I haven't quite thought about that. Any other questions? I guess.
So if you just look at the clusters are like within a factor of 5 of each other, can you do something?
So the sizes of the cluster? Yeah, so, right. So I only presented results when all the clusters have equal size. So these algorithms are fairly robust to those things too, but I don't quite know how badly it degrades with the skewness of the cluster sizes. Yeah, we didn't quite work that out.
Let's take further questions. There's food outside, so that's thanks, Aravindan.